A real pleasure for me to be here for many reasons. First of all, to face so many young students who are willing to come just before examinations to listen to lectures in a language that they normally do not listen to. I hope that you will interrupt me if there's anything that you don't understand, and you can ask your questions in Hebrew, because there are many people here who will translate them for you. I hope that you ask questions. You don't treat me like some visiting big shot whom you're too shy to ask questions from. That you will interrupt me the way you interrupt Professor Dagan, who is your normal teacher, and when something is not clear, either in the language or in the physics. So I've enjoyed coming to Israel very many times. I've been a great fan of Israel ever since when I was your age. I was lucky to work with some people who had just emerged from the wars of independence, and they had the strength of Ben Gurion, but also the vision of Weizmann. And Israel was a place which had that idealism and mixture of things which is particularly attractive. And it's particularly attractive for science. My mission as a teacher, and I have been fortunate to teach at my own university for 45 years, my mission as a teacher is to keep intact that human sense of wonder that is so essential to science, and which is so often knocked out when people serve in the army or when they go to university. I wonder, I mean, you look at the sky, let's see. Yes, you can see that actually. This is how I saw the sky as a young person on the Canadian prairies, where there were no lights from villages or whatever. And I could even see, with the good eyes I had then, that there were some objects which were fuzzy. This is Andromeda. And occasionally one was lucky to see something flashing across the sky. Now, all of these things for thousands of years had set people wondering. They built large buildings. Here is Stonehenge in England, with astronomical alignments. And near Stonehenge, there was another, even larger observatory, now largely destroyed. And they were built all across the northern hemisphere, 4,000 years ago. If you look at my own Western Canada, it is also full of 4,000-year-old stone rings. Now, these objects were built because people had this sense of wonder about what is happening in the sky. Not only about the sun and the moon, but also those strange objects called planets, which wandered across the sky. Now here I am today, that Professor Dagan has given me the privilege of telling you about a development which is perhaps the greatest single achievement of a human mind. Isaac Newton creating Newtonian mechanics just over 300 years ago. Now, Newton created mechanics. Let me first of all say, I called this in my title using a naughty word, an edifice of Newtonian mechanics. Edifice in English means a large building, a grand building, like a cathedral or a temple. And that is indeed what Newtonian mechanics is. Now, Newton was just a very remarkable person. So we have Isaac Newton, who lived from 1642 to 1727 and created many things. His father could not read or write. But he was sent to school, and even more fortunately, his father had died, and his mother married somebody who was rich enough to give him a booklet with paper on which he could write. And he did very well at school, and then went to, can you all hear me in the back? And then went to Cambridge, England, where he accomplished much of his work. In 1666, the Black Death or Plague closed Cambridge, and he went home and did some remarkable work at home near Lincoln. And in 1686, he published his Latin work, the Principia, to which I will be referring often in my 4 lectures. So I will be giving 4 lectures. The first lecture will be for you mostly a review of the laws of mechanics. And you have already encountered most of these: the conservation of momentum, the conservation of angular momentum, and the conservation of energy. I will be setting the stage for the very important story I want to tell. In the second lecture, I will be introducing to you ideas about the force of gravity. And that's in this, after the break this morning. In my third lecture, I want to talk about what was the most important problem of all, the Kepler problem. How the planets moved around the sun in elliptic orbits, or the comets moved in elliptic orbits. And 4, I will continue that and also talk about the Kepler orbits, which introduced the 20th century of science, which is the Rutherford scattering. The last 2 lectures, for which I've developed a simplified treatment for first-year classes, you can pick up a copy of almost everything I'm going to say at the break, and I have, I think, enough copies for you here. And so my last 2 lectures, you will not need to take notes, but those of you who want to take notes, especially on the second half today on gravity, I will encourage you to do so. Okay, now to go. Oh, I didn't realize this was glass, and I was supposed to use. I have transparencies here. I thought there would be a roll here, so I have written on the glass. Maybe I can erase it. Does somebody have a solution for that? Will that erase it? Okay. Oh. Okay. Thank you. Toda rabah. Okay. 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 Thank you. Now, so this grand building of Newtonian mechanics, let me call it with this new word for you, the edifice. The grand building has 3 important foundations. One is F is equal to MA is equal to M d2R dt squared. The other one is the universal force of gravity, Fg, which is a constant times 2 masses, m1, m2, over the square of the distance between them, times a unit vector in the direction between the 2 masses. And the final piece of the edifice is, of course, Newton invented calculus, which is the natural language of science. All of these together gave the clockwork universe in which explained just so very much. Now, we will be able to see in my lectures some of the fine details which Newton was able to explain. He didn't have a bicycle, but he could have explained the stability of a bicycle. But he did know about the precession of the Earth's equinoxes and many other small problems. Everything was explained. All motions were explained by the combination of these things. And in particular, the mysterious elliptic orbits of the planets. Now, this edifice of Newton's remained intact for about 250 years until Einstein in 1905, he enlarged it. He didn't replace Newtonian mechanics, he enlarged it. That doesn't seem so long ago, at least not to me. When I was your age, I was in Princeton and I was lucky enough to hear Einstein's last lectures. And so he was really a man still of the last century. And Newtonian mechanics had changed, had existed for hundreds of years before that, and still, of course, exists. Now, in order to do this, you must understand what it was about Newton that was so great. Because he had to not only invent the mathematics, the calculus, but he had to invent the concepts of mass, of momentum, of space and time. Before that, people had never thought about time except that you marked yesterday and today and as a continuous thing. All of these concepts he had to clarify, and when he wrote down these laws, then suddenly so much fell into place. The important thing about Newton is that basically he invented Western science as we know it today. Before that, people had asked for centuries about how the planets moved, but nobody asked why. The answer was thought to be that God moved the planets in the way that they move. He said, Newton, there is a force. Things do not move unless there is a force, and there's a universal force of gravity which explains the motion. So he asked not only how they moved, but why. And the fact that he asked both of those questions really, in a sense, created science as we know it today. So we want to look now at that construction of Newton's, and I want to talk to you about what Newton did. Now, the agenda, of course, says we have a second derivative to describe the motion, so we have to integrate twice. To solve the motion. Now, that would be fine if we had forces which depended on the time, and therefore accelerations which depended on the time. In such cases, you simply integrate in a straightforward way twice. But of course, forces more often depend on distance, and then you have to be more clever. You still have to integrate twice, and we will show you how those integrals are done in the cases of the Kepler orbits. But you have to be a bit more clever, and that's where the things like the conservation laws come in. But let me tell you right away what the good news is. The moment you write this down, you people are all liberated to solve any problem at once. You can learn calculus for years and obtain sophisticated answers. But by taking numerical approximations, you can solve any problem. And that includes a large range of problems for which the calculus doesn't help you, for which you must use computers, such as the trajectory of rockets sent to Mars, or indeed the history of our solar system. Well, let me just take a brief digression about this question of numerical integration. So, because I wasn't spelling it right. Integration. Solving problems numerically. Now, here, in order to do that, I'm going to show you an example of a problem. Let's say, here's the Earth, and you drop an object from 2,000 kilometers above it at the north. Let's do it at the North Pole so the rotation of the Earth doesn't matter. And so you drop this object, and the question is, how long does it take until it reaches the Earth? Well, we have here the gravitational force and an initial distance, let's call it R initial, and we have also final distance, R final. Now, the problem here, of course, is that the acceleration due to gravity for distances as large as this is not the same. Here, at this point, we have g is equal to 9.81 meters per second squared, the acceleration due to gravity. Here, at this height, we have 5.76 times meters per second squared. It is not constant acceleration. In high school, I think it is true in Israel as well as in Canada or North America, everybody has drilled into them these laws of constant acceleration because they're so simple, but it is not what applies in this case. Now, what you can do in any such problem is reduce it to the simplicity of constant acceleration simply by taking small steps. So you take small steps, delta t. You use the spirit of calculus, and in these steps you have, in each step, you have a change in velocity. Delta v is equal to minus g, whatever it is, times delta t. And delta x, the distance you move, is equal to minus v delta t, whatever the velocity is. These are laws of constant acceleration. If the step is small enough in time, then the constant acceleration will apply. And here, if I were to take this g and apply constant acceleration to the whole journey, I would get t is equal to 839 seconds. If I were to take the larger acceleration, it wouldn't take nearly as long. It would take 639 seconds. Now, the true answer must lie in between those two. And that's why you must integrate it numerically. And you can do that. You can take the fall, and on any one of you could on a desk computer, start out with zero velocity, find at that initial acceleration what how far you moved and what the change in velocity was. And after you finish the step, you calculate the new g, because you've moved. And you continue that. And if you do that, you get, if you were to take with delta t equals 10 seconds, these are small steps, you would get t, the time to drop is about 805 seconds. Now, this is important for two reasons. First of all, let me say that the same method can be used now, and you have this liberty to, you can all be space engineers. You can calculate the motion of a rocket going to Mars or anywhere. You could even, and people have done this, used large computers in small steps, say of a second, to trace back the history of our universe, to take every object of our solar system, every object, all the forces acting on it, and take a small step, and then see how it moves. And then after each second, you take, and each of the objects moves again, and you repeat that, and you can trace. We've been able to trace the history of our solar system back to millions of years at the time when the asteroid belt formed in between two of the planets and whatever. And that's a very interesting thing to do, and we can also tell what the future of our solar system is going to be. And so you already are now space engineers, because you don't need the techniques of elegant calculus to move ahead. But let me tell you that this particular problem can be solved elegantly. And we'll see in the lecture later today that the answer is actually, if u is equal to r initial over r final, then the techniques of integral calculus will tell you that t is equal to 2 times g0, which is 9.81, times u to the minus 3, the radius of the Earth to the minus 1, times u to the minus 1, u minus 1 to the 1/2, and then we have plus 10 to the minus 1 of u minus 1 to the 1/2. That complicated expression, which works out to be 804.7 seconds. So calculus, learning the techniques of integral calculus is helpful, because there are problems in which you do not have constant acceleration, which you can solve neatly without having to do them numerically. But of course, the majority of problems in the real universe have to be solved with computers. And you can do that, all of you can do that already at once, and by the methods that I mentioned. I want to go on to talk about the things, and to review for you the things that Newtonian mechanics does. And there are basically 3 important conservation laws. They all flow from F is equal to ma. Out of F is equal to ma, an idea that was around already somewhat before Newton. Galileo and others had postulated about things remaining in uniform motion unless something happened to them. But that's basically what F is equal to ma does. But Newton postulated the concept of space and time much more clearly, and wrote down the law, and also then wrote down the law of gravitation and the mathematics calculus to go with this. Okay, and so the first law, which you have certainly covered in your courses already, was the conservation of linear momentum. And this is a law. Simply you write F is equal to dp dt, because p is mv and ma is dp dt. And in fact, in this form, the momentum law applies even in when we deal with relativity and when we enlarge Newtonian mechanics. But it is particularly useful in dealing with systems of particles. It's an inexorable law. There I go again, using a big English word. A law which you cannot, under any circumstances, break. You must face momentum conservation. And even in things as complex as when a rocket shell falls on Israel, all of the pieces fly off, they must add that if you're a scientist, you go there and look at all of the pieces and see that in fact they followed Newton's laws and dispersed so that the momentum of the exploding shell conserved all of the momentum it had originally. Even violent things must conserve momentum. Now, I will not be needing momentum conservation so much, so I will not dwell on it, although there are so many topics, from rocket propulsion to collisions of particles, which deal with momentum momentum conservation. The second law is, of the three laws, is conservation of angular momentum. And I know that in the first year class you've just been dealing with that, and therefore what I will say will be not unfamiliar to you, and you can deal with that, because also we have the torque is equal to dl dt, where L is equal to R cross P, and the torque is, of course, R cross F. Now, this law which says, when you talk in the language of calculus, it says, in the absence of torque, the angular momentum is constant. Just as in the absence of forces, the momentum is constant. Torque is also very important because for central forces, which gravity is along the line. It's a force along the line joining two objects. And therefore, if F is parallel to R, there is no torque. So central forces such as gravity and electricity don't constitute any torque. And unless you make a solid object, for instance, I think you were introduced to spinning objects like the Earth or like a top on a table, which can precess because gravity can cause it a change, can exert a torque on the center of mass of a rigid object. But for a simple object all by itself, like a planet in the sky, the central forces mean that there is no torque. And therefore, the angular momentum is constant. Now, we have here for the angular momentum, we have L is equal to R cross mv, and this tells us that L, the amount of angular momentum, is mRv sine theta. That is, we have an object, here's the sun, here's a planet moving in some direction, then, and this is the force now along here, along the radius vector, and if this is mv, and then this is the angle theta, and we can always draw a perpendicular distance to the r vector. Let's call that h. So this is equal to mvh, where h is equal to r sine theta, and we call it the perpendicular distance. Now, I will use that variable, the perpendicular distance, h, in my simplified treatment of the Kepler orbits. And so I will want to remember the definition of angular momentum in terms of r cross p. Okay. The other conservation law, which is also very important, the third one, is energy conservation. Now, let me remind you of how it flows from F is equal to ma. Because this says I can now take and multiply each side in a dot product with the velocity. F dot v is equal to ma dot v. And the dot product, of course, commutes, and so we can write this as mv dot a. And then we have here f dot dr dt is equal to, now we have mv dot dv dt, and we can cancel out the two dt's, and we have left that f dot dr is equal to mv dv, which is a scalar. And this is a scalar. Both sides are a scalar. And this dot dr here, yes, that's, thank you, Avivi. Look, you people should pounce on me. And in my class at the University of British Columbia, I usually give large coins to people who find me making errors on the screen. And so if you want to get rich, here, yes. No, you are already rich. Okay. Now, out of this then comes that if I integrate both sides, then, of course, I get f dot dr. I will take some path here, a path, and this will be r1, and this will be r2, and I integrate along that path from r1 to r2, and that's equal to 1/2 times the integral of v dv from the velocity at the first point to the velocity at the second point. And this, of course, tells us, we call this the work done by the force. And the half doesn't come yet, comes from the integration, yes. And this is equal to 1/2 mv2 squared minus 1/2 mv1 squared, and we call this the kinetic energy change. And this is the negative of the potential energy change. And we get out of this that there are scalar quantities called mechanical potential energy and mechanical kinetic energy, which are conserved and they are not conserved under any circumstances. They're conserved when they are conserved. If there's friction or other dissipative forces, then mechanical energy isn't conserved. But of course, if we take all forms of energy into account, heat losses and even mass changes, then energy conservation remains a strong principle. But for mechanical energy alone, we have the principle that the principle which says that 1/2 mv2 squared plus the potential energy at R2 is equal to 1/2 mv1 squared plus the potential energy at R1. And so changes in kinetic and energy, in total energy, unless there are dissipative forces, the total energy, kinetic plus potential, remains the same. Now, energy is a tricky concept. Newton never got it right. He, in the Principia, he and others of his time thought that there was something like energy, but that it was proportional to the velocity, not the square of velocity, the kinetic energy. It was first got right by in about 1740 by a French woman, Madame Gabrielle du Châtelet. She was a rich woman of the French Enlightenment. She was the mistress of Voltaire, but she was brighter than Voltaire. And she was the one that translated and commented on the Principia, Newton's Principia, which then became popular in France. But she also first clearly stated the principle of conservation of energy, and she was an extremely able woman. Unfortunately, she had, when she was in her early 40s, she had a love affair with a young poet who was only 19, and she had a child, and childbirth was then almost universally fatal at that age, and she did die, but in the year before she died, she furiously wrote her masterpiece. She was 43 and wrote a book on mechanics, which for the first time properly clarified the concept of conservation of energy. And we're indebted to Madame du Châtelet for that clarification. Newton was able to get along and do all of the things without energy conservation, although we shall use it explicitly because it makes life so much simpler. Now, so energy conservation is then very important. Are there any questions at all about the three conservation laws? For you, all of you in the first year even, this is now review, because you've been dealing with all of these laws, have you not? Okay. Now, for the remaining 3 lectures, the rest of my time, I'll be able to go into new territory for you, because at least the first year students here have not really dealt with gravity before. And is that correct? You have not? You've not dealt with gravity. I'm just, can't you tell you how delighted I am that Yoram Dagan has left that topic for me? Because it is one of the most exciting topics to talk about to any class, at any level. It remains exciting because there is, of course, that wonderful, we'll also call it an edifice, which Einstein created 90 years ago, called general relativity, in which there is a new interpretation of gravity in terms of curvature of space. I cannot, unfortunately, talk about that. I will get one of these. Yes. And now we will deal with gravity. And for gravity, we have the force of gravity is equal to minus g, let's write it mm over r squared and then I'll put a unit vector along r. So this is a unit vector along r. So here we have the Earth and here we have an object going around it. Let's first of all take a satellite around the Earth. And so we have the mass of the Earth and the mass of the satellite, and the satellite is going around. Now, we know at Earth's surface we know that if this is equal to mg0, let's call it g0, the acceleration at Earth's surface, then g0 is equal to big G times the mass of the Earth over the radius of the Earth squared. And big G, the constant due to gravity, is 6.67 times 10 to the minus 11 newtons over, times meter squared times meter squared over kilograms squared. And so the constant of the universal gravitational constant, which Newton postulated. He postulated that there was something called gravitational mass, in terms of which everything was subject to a constant force of gravity. It puzzled him greatly because he had to postulate that the force of gravity acted instantly at a distance, and all his life that bothered him. We're not so bothered by it. Electricity does that too, and also, of course, we have Einstein's reinterpretation of the force of gravity. But action at a distance remained a philosophical problem for Newton. But that is nonetheless how he said things moved. And if we take these constants now, we know the mass of the Earth, this works out to be 9.81 meters per second squared. And that's a number, I think, that's familiar to you, isn't it? Yes, okay. To all of you. We know that acceleration right here due to gravity is that. Now, for the near-Earth satellite, we have constant velocity, and that constant velocity is equal to 2 pi RE over the time it takes to go around. But we also have Fg is equal to m times centripetal acceleration. The what? Yes? The satellite, we're talking the satellite right near the Earth, so it's at the radius of the Earth, okay? And many satellites are very close compared to the distance to the radius of the Earth. Now, this one has to be m v squared over RE, because the satellite goes round and around, and the force of gravity has to be exactly right to provide the centripetal acceleration involved in a circular orbit. Now, if we put these together, if we now put these together, we find that this is equal to 4 pi squared times RE over t squared times because we have v squared times m, and that's the centripetal acceleration. The v is 2 pi RE over t, and this has to be of course, equal to g, m times g, times the mass of the Earth over the radius of the Earth squared. The m's cancel out, and we find t, the time to go for a satellite to go around, is equal to 2 pi times the root of RE over G0. And that works out to be 84 minutes. A number we will encounter often again. That's about right. I mean, if you know that from what you have read about satellites going around the Earth, they take somewhere close to just under 90 minutes if they're at a few hundred meters, typically. And so it is simply a balancing of the gravitational force, providing the centripetal acceleration which is needed. Now, Newton, of course, didn't know about satellites, but he was wondering, how does the force vary with distance? And there were suggestions around from several people that maybe it was the square of the distance, and we'll find out reasons shortly about why the square of the distance is so attractive. It's because we live in three-dimensional space. But if the force varies as a square of the distance, how could you prove that? So Newton and the inverse square law. Now, what Newton did was that he compared the fall of an apple on his farm in Lincolnshire when he was sent home from Cambridge because of the plague. He describes how he watched an apple fall, subject to the Earth's gravity. And then he thought about the moon going around the Earth. There were no artificial satellites, but people already knew the distance of the moon. And they knew, of course, that the moon took 27.6 days or whatever to complete its retrograde orbit. And he took all of that into account and thought about it. And he said, we have the falling moon because it's going in a circular orbit, it is forever falling, but never getting any closer, because it is going in a circle. It has centripetal acceleration. And for the falling moon, he said, he knew that the Earth-Moon distance was equal to 3.80 times 10 to the 8th meters. And he knew, therefore, if it were inverse square law, then at the moon, G must be equal to what it is at the Earth times the radius of the Earth divided by the Earth-Moon distance, all squared. And this is a tiny number. It works out to be equal to 2.71 times 10 to the minus 3 meters per second squared. Many thousands of times smaller than it is here on Earth, at the moon. Now the question is that equal to the centripetal acceleration of the moon? And he knew the distance again, and then he calculated A centripetal is equal to V squared over R Earth-Moon for the moon. And what did he get? From the period of the moon, from the 27 days, you can get the velocity of the moon in its circular orbit. and therefore you can calculate the centripetal acceleration. And he found that this now works out to be 2.72 times 10 to the minus 3 meters per second squared. And he said then, Newton said in his old English, he says, it answers pretty nearly. And that convinced him that gravity must be an inverse square law. Now, let me tell you what's wrong with that argument. And that will take us on to a more detailed treatment of gravity. Here you have the Earth. He watched the apple fall. Now, I calculated G0 on the assumption that all the mass of the Earth is at its center. But the Earth, of course, is a solid object. And one piece of mass pulls one way and one another. And he said, how can I know that the Earth acts as though all its mass were at its center? It was the most important reason in his Principia why he needed calculus. He needed to solve that problem of saying that the whole Earth, a sphere, acted at its surface as though all its mass were at its center. And we're going to have a break now, and then I'm going to come back to that fundamental question. Okay. And please pick up this extra piece of reading for you for tomorrow's lectures. To convince himself that the Earth pulled an object near its surface as though all the mass were at the center. And let's explore that. And in order to do that, I'm going to do what Newton did. I'm going to discuss for you two Shell theorems. One says, if we have a uniform thin shell of mass, then it attracts a mass outside as though all the mass of the shell were at the center. So what we're envisaging here is a thin spherical shell of mass m, and here outside somewhere is a mass m. Now you can see, with calculus, you must take things in steps. If you can prove this, then the next step of saying the Earth is made up of uniform shells from where we're standing right to the middle, then it's easy to prove that the Earth as a whole acts as though all its mass were at the center. All you have to assume is something about the uniformity of the Earth. The shells don't even have to be uniform in density, but they all have to be, and they aren't. The mass at the center of the Earth is iron, and it's water mostly at the surface here, and so that the shells can have different total mass, but each of them has to be reasonably uniform. And that's the first Shell theorem. And the second Shell theorem says, if we have a uniform thin shell of mass, it exerts no force at all on any mass m inside. And that one will allow us to discuss the gravity inside the Earth. What if you drill a hole right through the Earth, right here in Tel Aviv, and jump through it? What happens to you? Well, it's easy to predict, and we shall. In fact, we won't do the experiment, but we shall at least discuss what would happen. And so these two theorems are interesting in their own right, and they do involve calculus. And so what we do in the Shell theorems is, first of all, now theorem 1, two steps. One, we split the shell into rings, and two, we add up all the rings. That's how calculus works. And so we're going to think of starting out with a shell, here we had it, and taking a ring of mass and taking a force on an object on the axis of the ring. That way we can use symmetry, which is so very powerful in mathematics and in physics generally. And so the first step for the Shell theorem then is, let me call it ring world. Here we have a uniform thin ring of mass, and on the axis we have a mass m. The ring has mass m. Now, if I call here, if I call this the x-axis, and this the y-axis, and this the z-axis. Now, this of course is then the little masses on the x-axis. And what is the force? Now, first of all, by symmetry, the x components, the y components, and the z components all cancel out in pairs. By that I simply mean, if I take a piece here of dm of mass, of course, here's the line r joining it. This is r. And the force of attraction is along the line r, which has a y component or possibly a z component. But if I take a piece at the opposite side of the ring, the x and y components will always cancel out. And so all I need to calculate the force on m, all I need is the x component of the gravitational force. And I need to add up all of those. And so we have fx due to dm, a piece here, the x component of the gravitational force is equal to minus g times m, the mass, times dm over r squared. And then, of course, we have to take the component by taking that angle times x over r, which is the cosine. That's the x component of the gravitational force due to the little piece dm. And now if I take fx total, every little piece along the ring has the same x component. And so the integral is trivial. And so we use symmetry to cancel out the x and y components, and therefore now we have the x component of the gravitational force is equal to minus g m times the total mass of the ring over r cubed times x. And that's equal to minus g m m x over, if the ring has radius r, that's equal to x squared plus r squared to the 3/2. There you have the gravitational attraction of a ring of mass. If you could isolate the ring of Jupiter, for instance, a ring of mass, this would be the kind of gravitational force you could expect as you approach it. And this kind of a ring world, I'll just digress for just a moment, because it has some interesting properties. And that's why I called it ring world. Now I say, what if x is very much smaller than r? That is, the mass here is close to the center of the ring. Well, if that's true, then we find then Fg is equal to minus g times the m times the mass of the ring, but x squared plus r squared is simply r to the 3/2 times x, because x is small compared to the radius of the ring. Now, what is the solution? What is the motion when you have a force like this? What is the motion in x? It's harmonic. All of you should have that instant reaction. The moment you have a force with a negative constant times the distance, the solution is a sine or cosine, and you get oscillations. And so, in this case, you get oscillations, and the period of the oscillation is t is equal to 2 pi times the root of r cubed over gm. And so, if the mass is near the center of the ring, it'll oscillate back and forth. Now, you can make science fiction films about this. Actually, in the laboratory, it might not be unimportant, because the Coulomb law is also an inverse square law. It's very hard to get protons up to relativistic energies near the speed of light, but it's easy to get electrons to the speed of light. So you can blow a smoke ring of electrons, and they capture the protons on their axis. They may oscillate a little, but you can accelerate the electron ring then, and they carry the protons with them in a very short distance to relativistic energies. And that's a neat way to get very high energies, but of course, nobody has succeeded in building anything that works toward getting you a large number of protons accelerated. So that's not the method that is used. But in principle, in our universe, you can do almost anything. Now, if we want to go now beyond the ring, there's a second step in calculus in which you simply take on the axis the attraction of each ring, slice the sphere up into rings. It's straightforward. Any first-year book on calculus, including Alonso and Griffiths, does it, and it then proves what was the big question. Does a ring of mass attract a mass outside as though all the mass were at the center? And the answer is yes. That's the precise answer you get from these two steps in calculus. I won't go through the calculus proof here, but I think you can read it easily, and I think you can understand what is involved in it. I'm going to be mischievous and talk a little bit more about the other theorem, which allows us to calculate gravity inside the Earth. Now let's talk about that one. Shell Theorem 2. Now here, we want to prove, which is actually a very profound observation, that if you take a thin spherical shell, it doesn't have any impact on any mass anywhere inside it. Now, why is that so? Well, let's draw a shell. And we place a mass. Let's place it here. It's not in the middle. It would be clear in the middle by symmetry that it's being pulled equally in all directions. But everywhere else, it's also true. Why? Well, draw a little cone here through the center of the shell, and that cone intersects on the shell a little sphere. Let's call this R1 and this R2. Now let me say it in words first. What happens? This piece is closer, and with an inverse square law, because it's closer, the force is greater of each piece of mass. But by geometry, this piece of mass is bigger, even though the force is less. And these two effects just cancel each other. So what you have here is a force F1 and a force, well, they're actually in the opposite direction. No, that's the direction they're in, F2, which are equal and opposite. Why? Because, well, take any of these. Take F1, for instance. F1 is equal to G minus G times dm1 times m over r1 squared. And F2 is equal to minus G times dm2 times m over r1 squared. But r2 squared, yeah. Thank you. But dm1 over dm2 is equal to, this circle has a radius which is larger than the other circle by the ratio of r1 squared, because it's a circle, r1 squared over r2 squared. So these are equal to equal to r1 squared over r2 squared. And when you put those in and divide these two, the forces are simply the same. It's a simple geometrical proof. Now, in many fields of physics, this kind of a proof, this kind of a statement is very important for electromagnetism, where you also have an inverse square law force. We often don't use Coulomb's law, which is the force, the equivalent of Newton's gravity. We use something called Gauss's theorem, which talks about how a force flows out of a charge, which is a very powerful theorem, basically the same idea. And so, inside a shell, no force. And it has to do, as you can see from the proof, that we live in a three-dimensional world. In a three-dimensional world, we take a cone, the circle is r1 squared. And this is to some extent, the great importance of an inverse square law force in a three-dimensional world. And it just says that it is the fact that it's an inverse square law force in a three-dimensional world that makes this Shell theorem valid. Let me tell you another way, and here I will digress away from my main agenda about an idea and a concept in physics which uses basically the same idea. And this concept is called Olber's paradox. And it deals with a simple observation that any one of you can make anytime you're out on a clear night in Tel Aviv. You ask, why is the night sky not infinitely bright? Now, it sounds at first like a stupid question, but it is in fact one of the most profound observations that we can make as human beings. Who has heard of Olber's paradox before? A few. But let me discuss it for you, okay? And tell you why it is such an important question, and how it's related to what I just said about Shell Theorem 2. Let's take here a person with an eye looking out in space. And he's going to look out at our universe in a cone. And I'm now going to take and divide this cone into steps of the same length. That we call them delta r. And then another step of the same length, delta r. And then another step of the same length, and I will continue. Now, you will tell me, if the stars are all average stars, like our sun, which is very much an average star, and distributed randomly, there will be maybe 2 stars here, if this is a few light years, and then more stars here, and again more in the next step. Why more? Because in each step, the volume increases as r squared. Each star has a brightness which falls off as 1 over r squared. But in each step, as you look, step after step after step, the number of stars increases as r squared. And therefore, from each step, you should get the same brightness. And if the universe is reasonably uniform and infinite, you get infinite amount of light. Another way to say it is simply that if the universe is really infinite, every little corner we look at, our eye will fall on something like the sun, and the night sky should look like the surface of the sun. But this is Olber's paradox. Incidentally, Mr. Olbers, who did this in 1826 and thought he was very smart, didn't realize that many people had asked this question before. I think the first was Kepler in 1612, when Galileo first took his telescope and looked at the sky and saw many more tiny stars in between the bright stars that you could see with the naked eye. And Kepler said, but hold on a moment. Why is there not an infinite number of them? Why is there still, with your telescope, a void in between the stars that we see? Now, what's the answer to that? Who wants to tell me the answer to that? What do you think is the answer to that? Yes. Who wants to? Well, let me first of all tell you, it has nothing to do with absorption of by interstellar dust, and many other things don't have. People have looked at all possible causes, but the cause which is fundamental eventually is that there was a Big Bang, and we have an event horizon beyond which we cannot see. In other words, that's the end. And it is maybe a dismal psychological conclusion that, we live in something that, at least to our perception, is finite. But this question of why the night sky is not infinitely bright is a very deep question, which I would encourage you to Google under Olber's paradox and look at all of the possible explanations of it. I would also encourage you, if you meet people who are not in physics, whom you meet, relatives or friends on the street, and you ask them, why is the night sky not infinitely bright? And they will say, oh, you're one of those people in Professor Dagan's class. Okay. It would identify you as a physicist forever from now on if you are worried about that. And I want you all to worry about that when you get out. It's just as though you were on a little island and you were looking out at the ocean and seeing nothing else except what was right in front of you. Any comments or questions? Yeah. Well, not in an expanding universe. The event horizon is connected to the models of the universe we have too. And it wouldn't happen quickly, so don't worry about it in the next while. Any other questions about it? Okay. Well, I'm sorry for that digression, but there are in physics, often as you proceed through it, many very deep questions based on very simple observations, which will help to keep your sense of wonder intact. Okay. Now, I want to go next to talk about gravity inside and outside the Earth. Now, first of all, if I plot now the force of gravity as a function of the distance r, and here is the radius of the Earth. Well, we know now from the Shell Theorem 1 that outside it falls off as 1 over r squared. That's the force of gravity outside the Earth. What is it like inside the Earth? Now, inside the Earth, by the Shell Theorem, if we go inside, then the force of gravity at any point inside is equal to minus g times little m, the mass you have, over the distance from the center of the Earth squared. But what is the mass here? It's only the mass underneath. All the shells above you don't influence you at all. It's only the stuff lying below you. And so let me put here m of the core. And so the mass of the core, of course, is divided by the mass of the Earth is equal to 4/3 pi r cubed divided by 4/3 pi times the radius of the Earth cubed. That's how much is left, because it's the mass of the sphere, the volume of the sphere is 4/3 pi r cubed. And so, if the Earth is uniform, has mass, it isn't, of course, but if the Earth is uniform, then the mass of the core decreases as the cube of the distance. And so we find then that the force of gravity is equal to minus G0 times R over RE. At the Earth's radius, we get G0, 9.81. But it falls off with R. And so for a uniform Earth, I would draw it like this, inside the Earth. And it's proportional to R. Now, in actual fact, oh, thank you. In actual fact, because the center has more iron in its ocean here, the density increases, it goes something, you can see it in many places like this. It falls off, not quite that way. It does fall off, and the center, of course, the question, now you drill a hole right through the Earth, and you jump into it. What happens? We're going to insulate ourselves from the temperatures inside and whatever. It's not a very engineering, from the point of view of engineering, it's not a very easy thing to do. And so, what is the period? T, the period, you jump into the hole and you come back to where you were in Tel Aviv. The period is equal to 2 pi times the square root of RE over G0, and that's equal to 84 minutes again. It's the same constants exactly as the satellite going round and round. You could get the same kind of thing if right here you built a pendulum so tall that the pendulum had the radius of the Earth, and you watched this pendulum go back and forth. For that pendulum, for the mass swinging back and forth, it would be 84 minutes to complete an oscillation. Just because the same constants, G0 and R0, are involved. And so, that's the answer to that question. But there is now a generalization of this which is easy to make. And this generalization is called the universal (42-minute), which is half of 84, subwave. Because let's say now we take the Earth, spherical Earth, and we drill a tunnel from A to B, which could be from Tel Aviv to Haifa, or from Tel Aviv to London, England, or whatever. Now, what is the motion? Well, you put rails and you put make sure there's no friction. Here you have a mass, m. Here's the force of gravity toward the center of the Earth. But if you have a tunnel, straight tunnel between 2 points, it's only the component along the tunnel which matters. So what is the component along the tunnel? Let's call this direction x. So we have Fg is equal to minus, the same as we had here, is equal to minus mg0r over Re. but FGX along x is equal to minus mg0 r over RE times we have x over r, and that cancels out, and this is equal to minus mg0 times x over RE. So the component of gravity along this, any straight line between any 2 points, is this, and the solution is the same as we just had for the hole right through the middle of the Earth. And so you will oscillate back and forth with a period, full period, back and forth of 42 minutes. But from here to Haifa would be 84 minutes. From here to Haifa, one way would be half of that, 42 minutes. So you can make a universal tunnel. Of course, again, you have engineering problems when in removing the friction so completely or whatever. But in principle, it's a very, very neat solution. Any comments or questions? Okay. So now I want to talk about gravitational potential energy. Now, we have, of course, delta U, the change in potential energy, which is all we can measure, is defined to be U of R2 minus U of R1. And this is equal to minus the integral from R1 to R2 of F dot dr. And this is equal to, if the force is negative, this is equal to plus toward the center as we're outside, the integral from R1 to R2 of mg0 times RE over R all squared dr. And so this is equal to minus mg0 RE squared times 1 over R2 minus 1 over R1. Now, all we can do with potential energy is differences between the energy at different positions. There is no absolute. But what we do in practice is make a choice. We say, we choose U of infinity equal to 0. So there's no potential energy when we're infinitely far away. And then we get U of R is equal to minus mg0 times RE squared over R. It falls off as 1 over R, the potential energy, not like the force. And so if we draw the potential energy, now versus R, this is U of R with that choice, and here is RE, the Earth's radius. We get something falling off as 1 over R, proportional to 1 over R, and at the Earth's radius, it has a value of minus mg naught RE. I could also take and integrate the potential energy inside, and inside it falls off quadratically like this, because the integral of R, it's proportional to R inside the force, is r squared. And so this is how it looks inside, and it falls off to minus 3/2 mg0 re. I'll let you do that for yourself, but this means now that if I take a cannonball and fire it here at the Earth and shoot it away, if I want it to go to infinity, there is something called the escape velocity. For that, we want, for the escape velocity, we have the energy is equal to 0. We fire it so that at infinity it has no kinetic energy and no potential energy, and that's equal to 1/2 mv squared minus g me over re. And then we find that v escape is equal to the square root of 2g, the mass of the Earth, divided by re, the radius of the Earth, and this is equal to 1.12 times 10 to the 4th meters per second. Now, we're trapped here in the potential energy. We're in this well. We're sitting here. It takes a lot of energy to boost us away to infinity. That's why we need powerful rockets. It takes half as much energy to get you to a near Earth satellite as it does to get to infinity. But to fire anything to infinity is not easy. And that's escape velocity. Now, we're more trapped than that. If you take our solar system and want to get away from the sun, we know our distance from the sun, and you find that the velocity is about 3 times greater, the escape velocity from the solar system. The kinetic energy you need 10 times greater. If you want to get away from a neutron star, forget it. But you can calculate getting away from our galaxy, for instance. Again, you need a very high velocity, much higher than to get away from Earth. Now, let me tell you about that. A sad story. I had a Canadian friend, an engineer called Jerry Bull. He was interested in supercannons. And about 20, 30 years ago, he became the world's expert on building cannons. He was even able to shoot a few objects up into space, into orbit. Now, people didn't want his technology for that purpose because they found the rockets were much better than cannons to achieve communication satellites and other things. Well, to cut a long story short, my friend Bull became a shogunate. And he decided nobody wanted him. He would sell his services to Saddam Hussein. And so he built some super cannons in Iraq. And then he was in a hotel room in Belgium, and somebody shot him. I think there are times when it is necessary to do that sort of thing, and there are times also when the Mossad can be very effective. And so he is no more, my friend. But it was not a good idea. I mean, you live here in a country in which you have to think. In Canada, we never worry about such problems. We produce the idiots that sometimes that can do these things. But he was Meshuggah and needed to be done away with. Anyway, let me finish today with one of the things I started with. Remember when I dropped that object from 2,000 kilometers and I got the complicated expression? Well, how did I get that? Now, we're going to drop an object again and solve it by integrals. That was the numerical question I gave you. Remember, the answer was 805 seconds. Well, now, to show you how, in general, when we have f is equal to ma, we need two integrals to solve the problem. Energy conservation is one of those integrals. So here, for that problem, we can say that E over m, the energy per unit mass, which is a constant, is equal to minus g, mass of the Earth, times over r initial. That is the Earth's radius plus 2,000 kilometers. That's because at that point we drop it. It has no velocity, no kinetic energy. Then it acquires kinetic energy. But we can also say E over m is equal to 1/2 v squared minus g me over r. And from this, we get v, which is defined to be dr dt, is equal to v, the square root of 2g me over r minus 2g me over r initial, which is a number. It depends on r, the velocity, but now I can find that dt, if I integrate both sides, I take dt, which is t, is equal to the integral of dr over that square root. And that's the answer. I gave you the answer in terms of inverse tangents and many other things. It's not a trivial integral, but it can be done. And so the same problem, which I said, solve it by numerical integration in steps of 10 seconds, you can do it analytically with the techniques of calculus, and calculus teaches you how to do. Many of you already would know how to solve that integral with calculus, and you can try to do it. I gave you the solution. And so there are many problems for which using calculus is very helpful. And then because we get exact answers without having to use computers. But also we always have that liberty that we can solve any problem numerically if it takes us too much time to perform a complicated integral. Any comments or questions? Well, I'm going to go on tomorrow about the most exciting bit of all. This is to tell you about the elliptic orbits and how to explain them. Almost every first-year textbook, including yours, says basically, if you were more intelligent and knew more calculus, we would prove this for you. But you're going to have to assume that somebody is somewhere smart enough to do it. Well, you're all smart enough, and I plan to show you a very simple proof, which tomorrow, which is in that paper I gave you, which can be understood by even a high school student, about how that elliptic orbit arises. It is the most important piece. It is the crowning piece in Newtonian mechanics, because for thousands of years, people had puzzled about the planets. I mean and about how these things moved, about how these unusual stars moved. Some people even, they say that some wise men came somewhere nearby here and were attracted by some of the stars that moved in a funny way. So people wondered about them. Well, with Newton, the wonder went. The wonder in our world is still there, but the puzzle of how the planets moved became understood. That's for tomorrow. Thank you.